Hello everyone, I'm J Wildberger, and I'm going to be extending this novel arithmetic of ours based on multisets, what we might call box arithmetic, in the direction of negative numbers, which we got at by introducing anti-msets, a rather novel arithmetical feature that somehow mysteriously parallels the world of modern 20th century particle physics with the particle-antiparticle duality or symmetry that seems to pervade the physical world. Perhaps something parallel to that actually sits at the heart of mathematics as well, even though it hasn't really been explored very much. So today we're going to have a closer look at all this interesting arithmetic with some examples. Okay, so let me just remind you that the setup is that we're starting now with our zero world consisting of two objects, not a single zero, which is the empty mset, but also the anti-zero, denoted with the same notation but with a superscript a. And I'm also going to introduce some possible variants that we could use in some situations. One being just to replace the black bounding brackets with red bounding brackets, parallel to what an accountant would do in terms of black and red representing positive and negative assets, liabilities. And perhaps when we're using sort of in a typed situation with just on a line, we could also perhaps introduce braces, just a suggestion, to give us an alternate way of representing anti-msets. Okay, then we had these two very identical tables for the addition and multiplication. 0 plus 0, 0, 0 plus anti-0 is anti-0, same thing here, and anti-0 plus anti-0 is 0. And exactly the same actually for the multiplication. And curiously, especially here, this gives us this unusual law that 0 times anti-0 is anti-0 rather than 0, which contradicts our experience that 0 times anything is always 0. So this makes us a little bit uneasy. This is certainly a different kind of arithmetic than we're used to. And as some viewers pointed out, this also can be leading to a failure of the distributive law at this very elementary level with just zeros and anti-zeros. So for example, if we look at 0 plus 0 times anti-0, well, 0 plus 0 is 0, so that's going to be exactly this. We're going to get anti-0. But on the other hand, if we look at 0 times anti-0 plus 0 times anti-0, this one's an anti-0, this one's an anti-0, and according to this, the sum is then going to be 0. So the usual distributive law, just at the level of these zero objects, is not going to be valid. Now that does not mean that the actual arithmetic that we're primarily interested in, having to do with numbers and polynumbers and multinumbers, etc., is also necessarily inconsistent. But it just means that we do have to be rather careful about questions of the logical structure of things. And ultimately, we want proofs and perhaps models of this that will ensure that what we're doing is logically consistent. At this stage here, it's exploratory, and in that spirit, we're going to give you some examples today of these anti-msets that are built up from this anti-zero, and also then negative numbers and then integral polynumbers and integer polynumbers, extending the negativity into the world of polynumbers. So in some sense, this is like an assembly language approach to arithmetic. We're going really right down to a sort of a fundamental level here and uncovering structure that's a little bit unfamiliar, even though it does lead to pretty familiar arithmetic. But we get to look at that arithmetic in a new light. Okay, so last time we saw that as a consequence of having anti-zero. We should probably extend this anti-notion to msets very generally, so that for any mset or object m in this arithmetic, there's going to be an anti-object, which we denote by m super a, okay, which has the property that if m and anti-m are together in an mset, then they cancel out, just like an electron and a positron. And we just get an empty mset as a result. And we also saw that this ma, this anti-m, can be evaluated by essentially adding the anti-zero to m in either order. And in particular, this shows that the ante of ante-0 is 0. And extending that sort of black-red approach to notation, let me suggest that we could use the following sort of two-dimensional version of that. So if here's an M set, M, okay, it's a box with a couple of boxes in it. This is an empty box. This box here has two empty boxes in it. Okay, so this would be what we would usually call, this would be like 1 plus alpha squared in polynumber language. If we wrote it out in terms of linear structure, there's a big M set with an empty M set there, and here's an M set with two M sets inside it. So if we were looking at this M set and trying to understand its anti-object, so M super A, then I propose that we could denote that with a red bounding box. So we take this thing here and we copy it essentially, with the distinction that the outside box, the containing box, is now red instead of black. But the interior things are just the same as they were over here. And in the linear case, that would involve replacing these outside brackets with red brackets instead of black brackets. But crucially, what's inside stays the same. Now, if we didn't have colors at our disposal, okay, then we could replace these red brackets with, say, braces or whatever else we wanted to use. But I like this two-dimensional representation because our minds are very much oriented to two-dimensional visualization and understanding. And so this makes demonstrating things a little bit easier for us. If we have too complicated something like this, it's fine for an AI or a computer, but our physiology prefers to see things in this form here. So this is actually quite a useful way of illustrating some things. Okay, so the first use of these anti-objects is to define -1, or I like to write 1 bar. So 1 bar, or -1, is the M set consisting of a single anti-0. And it has the property then that if you add 1 bar with 1, then you're going to get a 0, or the empty set. And then the multiplication of 1 and 1 bar follows this sort of familiar pattern. And then we can extend this negation to natural numbers. So if n is a natural number, then we can define n bar, or -n, to be 1 bar times n. And that then introduces an extension of our fundamental objects from natural numbers to integers. So we create integers by multiplying natural numbers by -1. So now we have a wider framework. And it's really this wider framework that is a very pleasant environment with lots of interesting applications. And furthermore, if we have a more general M set, a pure M set M, then we can define its negative also, M bar, or -m, exactly in the same way. We just multiply by 1 bar. So I remind you that in this world we can always add and we can always multiply M sets, okay? There's no requirement that these things necessarily be numbers. Those are just the top level things, that there's a whole range of different, more complicated kinds of objects, and these operations extend to all of them. And then we also saw that another way of thinking about this M bar was that it consists of the M set whose elements are the antis of all the elements of capital M. So it's the M set of MA as M ranges through capital M. So let's do some examples of some simple integer arithmetic. 2 plus 1 bar plus 4 bar. Well, 2 is the M set consisting of 0, 0. 1 bar is the M set consisting of just a single anti-0. And 4 bar is anti-0, 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 anti-0. When we add them, we just dump everything out into a single M set. So we get 0, 0, anti-0 here, and then a bunch of anti-zeros further. And then once we have them all in an M set, then the zeros and the anti-zeros will mutually annihilate each other, okay? So say that pair will disappear and that pair will disappear, and we're left just with anti-0, 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 which we recognize as 3 bar, or -3. Good. Okay, what about 3 times 2 bar? Well, 3 is 0, 0, 0, and 2 bar is anti-0, anti-0. How do we multiply these? Well, we have to form the big M set consisting of all possible sums of elements here with elements here. So we have to be able to evaluate 0 plus anti-0, which we know is anti-0. And there's going to be 6 possible such things. So we're going to get that thing, which we recognize as 6 bar. Okay, let's illustrate the fact that multiplication and in fact addition also are not essentially binary operations in this world. They're in principle things that can input a whole bunch of things at the same time. So let's multiply 2 bar times 4 bar times 1 bar. So that's anti-0, anti-0. There's 2 bar multiplied by anti-0, 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 anti-0. There's 4 bar multiplied by just anti-0. That's 1 bar. So what are we going to have to do? We're going to have to take a multiset which consists of all possible sums of elements here with elements here. Okay, so we're going to take one of these anti-zeros, one of these anti-zeros, and one of these anti-zeros, and we're going to add them. So over here, as an aside, let's just compute this thing, anti-0 plus anti-0 plus anti-0. Well, anti-0 plus anti-0 is 0, and 0 plus anti-0 is anti-0. So this just gives us anti-0. In fact, more generally, if we had k anti-zeros all added together, then whether we get 0 or anti-0 as the final result depends on whether k is even or odd. If there's an odd number of anti-zeros, we're going to get an anti-zero. If there's an even number of anti-zeros, we're going to get a 0. And because the addition and the multiplication tables are the same, that's the same statement if we replace the additions here with multiplications. So anti-0 times anti-0 times anti-0 is also going to be anti-0. Okay, so it's clear what we're going to get here. We are going to get a whole bunch of anti-zeros. A whole bunch of them. 1, 2, 3, 4, 5, 6, 7, 8. And so the final result is 8 bar. Okay. So now we can convince ourselves that the arithmetic that we've cooked up here really does obey the same rules as our usual integer arithmetic with respect to the operations addition and multiplication. Okay, so let's go down one level to the polynumbers. So I remind you that a polynumber is an M set of natural numbers. So let's look at examples. Here's an M set of natural numbers. P is the M set 0, 0, 2, 2, 2, 5. These are all natural numbers, and this has an interpretation in terms of sort of more usual notation as 2 plus 3 alpha squared plus alpha to the 5. And if we connect with my usual preferred notation for polynumbers like we use in the algebraic calculus course or that we've talked about extensively in the Math Foundation series, we can think of a polynumber, just like a polynomial, as a list, a vertical list, say typically, of coefficients. The actual variable itself is sort of secondary, it's sort of implicit. It's really the coefficients that are the crucial thing. So here there's a 2, there's 0 alphas, 3 alpha squareds, 0 alpha cubes, 0 alpha to the 4th, 1 alpha to the 5th. So let me just point out again the important distinction here between this more classical approach to what a polynumber is, namely as a list, okay, and this new point of view, this M set point of view towards what a polynumber is. Okay, so these are closely connected in the sense that this thing here is really the multiplicity list for this M set. This is keeping track of how many of each of these objects we have, because the objects appearing here are naturally ordered. They're natural numbers, so 0, 1, 2, 3, etc. So we can encode this information just sort of by counting how many zeros there are, how many ones there are, how many twos there are, how many threes there are, etc. But there's a sense in which this is actually a more basic or fundamental object, okay? Because the ambiguity that's appearing over here, that you're allowed to add additional zeros below wherever you are and doesn't change, that is sort of removed at the multiset level because we don't have to say that. We're just talking about a multiset. So this is a subtle but important shift that I do want you to take on board, that perhaps a polynumber is really, sort of more fundamentally, an mset of natural numbers. Okay, so now we want to enlarge that view because now we have integers. Okay, we have integers. So let's see what happens if we extend this notion to involve integers. So here's the negation of this p. Okay, how do we negate an mset, or p bar or minus p? Well, we just take the ante of each one of these. So we have 0 ante, or anti-0, anti-0, anti-2, 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 anti-5. And that's also a polynumber, a familiar kind of polynumber, but one involving negative coefficients. So if we wrote it out as a polynumber in alpha, it would be 2 bar plus 3 bar alpha squared. So there's really 3 alpha squared here, but there's antis here, so it's representing 3 bar alpha squared and 1 bar alpha to the 5. And as a vertical list, we could write minus 2, 0, minus 3, 0, 0, minus 1, or I prefer 2 bar, 0, 3 bar, 0, 0, 1 bar. Notice also that I'm putting the 1 bar here. Okay, we're sort of forced to here because we don't have a subtraction operation. So it would be wrong for us to say minus alpha to the 5. Not wrong, but not really consistent with what we're doing so far. So far we really only have addition and multiplication. So strictly speaking, to be consistent, we probably also should put a 1 here. Okay, it's probably a little bit more consistent if we treat all of these things sort of uniformly and, you know, treat the 1s the same as the 2s and the 3s. I suppose we could even go one step further and write zeros, 0 alpha, etc. But that's maybe going a bit too far. But anyway, so this is the negation of this thing here in sort of an obvious way. But so we're also allowed to mix and match these things. So if we can have a situation where we have a polynumber which has both positive and negative coefficients. For example, this q thing here, have a look at it. It's msets 0, 1a or anti-1, 2a, and 3. So as a polynumber, this would be, well, there's a single 1. There's a 1 to the a here, so that's like 1 bar times alpha. And there's a 1 bar times alpha squared, and there's a 1 bar times alpha cubed. So what would happen if we added, say, p and q? Well, we have to put them all together in a big mset, okay? So there's a 0 here, a 0 here, and a 0 here, so it'll be 3 zeros. There's a 1a, there's a 2, 2, 2, we'll put 2, 2, 2 in, and we also have to put a 2a in, an anti-2. But that 2a is going to cancel with one of the 2's. Okay, so they're going to go, so we're just going to have 2, 2, and then we get a 3 and also a 5. So the result would be 3 plus 1 bar alpha plus 2 alpha squared plus 1 alpha cubed, if we wanted to, plus 1 alpha to the 5. And, you know, more colloquially, we would write this or say it as 3 minus alpha plus 2 alpha squared plus alpha cubed plus alpha to the 5. That would be the more familiar sort of high school way of saying it. But that does assume that we have a subtraction operation, which we're not assuming at this point. Okay? So that's the way anti-numbers generate negative coefficients. So it's the antis inside the brackets that are generating negatives sort of outside the brackets. Maybe that's one way of thinking about it. Great, so let's do a little bit of multiplicative arithmetic with these integer polynumbers. Say 2 plus alpha times 3 minus alpha squared. First of all, let's over here just draw a picture of this thing here. Okay, so what is 2 plus alpha? So it's a box that has what in it? Well, it's going to have two empty msets. So if we just had that, that would be the number 2. Okay? But it also has an alpha in it. What's an alpha? Well, an alpha is when you put a 1 inside this box here. So 2 plus alpha looks like this. And now we're multiplying it by 3 minus alpha squared. What does that look like? Well, that's also a box, okay, and it has a 3 in it. Okay, so it's the 3 zeros in there, that makes the 3. And then there's a minus alpha squared. So what does that look like? Well, an alpha squared would be like when you had a box here with 2 empty boxes inside, okay? But we have a minus alpha squared. So I actually need to change colors and introduce a red box because we have a minus alpha squareds. So I'm going to put a box here and a box here. Have a look at this. Okay. So if we didn't have this thing here, okay, if we remove those 3 things and just looked at this big black box with a red box inside it and 2 black boxes, this would be the negation of the thing that we got by replacing this red box with a black box. Okay, if we replace the red box with a black box, then we would have alpha squared. All right? So negative alpha squared, you get that by taking this thing here and changing the color of all the ingredients. In other words, replacing all the ingredients with antis. So the minus alpha squared is represented by this big box with a red box inside it containing 2 black boxes. Okay, so we could do the arithmetic at the box level. But so let's sort of do it in a more regular fashion. So 2 plus alpha. So what's this going to look like? So this is going to be an mset. It's a polynumber, so it's an mset of natural numbers, or these days integers. So 2 is represented as 0, 0, and the alpha is represented by the 1. Okay, and we have to multiply it. Here's another mset consisting of what? Well, there are 3 zeros in it. And then there's a minus alpha squared. What's that? Well, that's like a 2. That's sort of representing alpha squared. But we have to put an anti-2 there because we have minus 1 of them. Okay, so let's see if we can do this calculation. So there's quite a lot of terms here. There's 3 times 4, so it would be 12 things altogether. So what do we have to do in order to multiply these 2 things? Well, we have to take all possible sums. Okay, so 0 plus 0 is 0. So I'm going to do 0 times all of these. So I get 0, 0, 0, 2a. I'm just adding 0 to all of these. Okay, I have to do the same thing with this 0. Add 0 to all of these. Now I have to do the same thing with this one. Add 1 to all of these. 1 plus 0 is 1. 1, 1. And 1 plus 2 alpha. So that's interesting here. So we need to calculate over here, perhaps in a different color. So what is 1 plus 2a? So 2a. So another way of thinking about that is it's 1 plus 2 plus anti-0, right? So the anti of 2, okay, one way of saying what that is, it's 2 plus anti-0. So if we write it this way, and sort of we use distributivity, we would get 3 plus anti-0, which is anti-3. So according to that calculation, we should have a 3a there. And in terms of an actual, polynumber, what polynumber is this? Okay, so we get 6 zeros, so that's 6. We have these 3 1s here, so that's like 3 alpha. And then we have these 2 2a's, or anti-2s. Okay, so that's like alpha squareds, but with a minus, so minus 2 alpha squared. And this 3a, anti-3, corresponds to minus alpha cubed. that look like what we expect? 2 times 3, 3 times alpha, yes, minus 2 alpha squared, yes, and minus alpha cubed. Good. Let's do another example. Say 1 minus alpha cubed. Okay, so that's going to be what? Well, 1 minus alpha. As an mset in the sort of more familiar way, that's a 0 representing the 1, and the minus alpha, it's like a 1 but with an A here, okay? Anti-1. Okay, so times 0 anti-1 times 0 anti-1. All right, so we're going to get an mset consisting of all possible triple sums. Element here, element here, element here, adding them up. Okay, so there'll be like a 0 plus 0 plus 0, that'll be 1, and then there'll be a 0 plus 0 plus 1a, okay, and then there'll be a 0 plus 1a plus 0, there'll be a 0 plus 1a plus 1a, that's 4 of them. And then with the 1a, so 1a plus 0 plus 0, 1a plus 0 plus 1a, 1a plus 1a plus 0, and 1a plus 1a plus 1a. Okay, what are we going to get when we do all this? Okay, so the first thing here is 0 plus 0 plus 0, that's going to be 0. What's this thing here? 0 plus 1a, so that's going to be 1a. And in fact, so is that, and so is that. So we're going to get 1a, and so is this one. So it'll be 1a, 1a, 1a. So I dealt with this one here, this one here, this one here, and this one here. Okay, what about this thing here? 0 plus 1a plus 1a. Well, what is 1a plus 1a? Anti-1 plus anti-1. Well, let's do a little sum over here, okay? So anti-1 plus anti-1. Okay. Well, one way of thinking about what an anti-1 is, it's 1 plus anti-0. So maybe we could write it like this, okay? That makes it clear that this is 2 plus anti-0 plus anti-0 is 0. So we're getting 2. So anti-1 plus anti-1 is 2. It's the same kind of story with the parity. There's an even number of antis, and so we're getting something that doesn't involve antis. So this thing here is going to give us a 2, as is this one and this one. Oh, sorry, not plus, just a single 2, and also another 2 and another 2. And finally, this last one here, anti-1 plus anti-1 plus anti-1, same kind of story, but we're getting a 3 with an anti. And if we wanted to write that out as a polynumber, let's squeeze it down here, maybe in blue. So this is what? This is 1. There's 3 of these 1a, so that's minus 3 alpha, those things there. There's 3 of these, so plus 3 alpha squared. And there's 1 of these, so minus a single alpha cubed. So we've done a little binomial expansion in this mset world. Okay, but now we're able to move in a different direction, still staying in the world of polynumbers, okay? But we're going to use the fact that we have integers now in a more subtle, more expanding fashion. And this leads us to what we're going to call integral polynumbers, or perhaps one could say Laurent polynumbers, but I'm not going to actually use that notation. I'm going to prefer integral polynumbers. So an integral polynumber is an mset of integers. Polynumber, we said before, was an mset of natural numbers, like zeros, ones, twos, etc. Now an mset of integers. So, for example, here, P, here's an mset of integers. -2, -1, -1, -1, 0, 3, 3. And we can now interpret this in an algebraic fashion by being sort of consistent and thinking of these negative signs as just representing powers of alpha which have negative numbers as exponents. So this 2 bar here is giving us an alpha to the minus 2. These things here, these 1 bars, are alpha to the minus 1. There's 3 of them. The single 0 is a 1, and these 2 alpha cubed, these 2 3's give us 2 alpha cubed. So in terms of a box, here's a box that corresponds to this. So there's a box, okay, and it has a 2 bar in it. Where's the 2 bar? This thing here is essentially the 2 bar, because a 2 would look like a box, a black box with 2 empty boxes inside it. If we want to negate that, what we have to do is we have to take the mset, which consists of the antes of all the ingredients. So we have to take the antes of the 2 involved here. So this is what the 2 bar looks like. And similarly, the 1 bars here, that one, and that one, represented by a black box with a red box inside. The 0 is just represented with the single empty set. And the 3's, well, there's 3, and there's another 3. Now, what in terms of our sort of familiar notation for msets, if we just looked at the positive part of this, maybe I should put it down a little bit. Okay, let me write it like this. Okay, so we just looked at the positive part. There's a single 1. Okay, there's 0 alphas, 0 alpha squareds, and there's 2 alpha cubes. So that would be sort of our usual polynumber representation as a multiplicity list with just positive powers of alpha. But now we have also 3 alpha to the minus 1's and an alpha to the minus 2. So we can represent that by essentially going in this other direction, going up from this bar here. Okay, so there's 3 here in this position and 1 here in this position. Right? So this is sort of the alpha to the 0 position, alpha to the 1, alpha to the 2, alpha to the 3. This is alpha to the minus 1. Here's alpha to the minus 2. So this is sort of consistent with what we're doing previously, but we're kind of going in a different direction. So in my next video, I'm going to have to say more about how to think about these integral polynumbers, like what do they mean? How do we represent them, or how do we think about them? But let's just do a bit of arithmetic with them to give us an idea of how this works. Okay, so let's add 2 integral polynumbers. Here's an integral polynumber. 1 bar, 2. Here's another one, 3 bar, 1, 2, 4. To add them, we just make a big mset, dump everything together. So there's a 1 bar, there's a 1 bar, there's a 2, there's a 3 bar, there's a 1, there's a 2, there's a 4. Okay, so we could rewrite this maybe in a slightly more organized fashion like this. 1 bar, 1, 2, 2. Oh, there's a 3 bar as well. We could put maybe the 3 bar there. Okay, 3 bar, 1 bar, 1 bar, 1, 2, 2, and 4. Okay, and in terms of interpretation in terms of polynumbers, this would be here. This would be 2 alpha to the minus 1 plus alpha squared. Okay, that thing there. And this thing here would be an alpha to the minus 3 plus an alpha plus alpha squared plus alpha to the 4. Okay, whoop, round bracket. And what are we getting out of this? We're getting an alpha to the minus 3 plus 2 alpha to the minus 1 plus alpha plus 2 alpha squared plus alpha to the 4. Does that sound reasonable? Yes, I think it does. Okay, here's another example, a little bit more sophisticated now because we're going to combine these 2 rows of negative numbers in slightly different ways. Okay, so have a look at this thing here. 3 bar, 1 bar, 2 ante. 1 bar ante, 0, 2, 3. First of all, let me express the meaning of this in more familiar sort of polynumber language. What is this thing representing? It's representing the polynumber alpha to the minus 3 plus alpha to the minus 1. And without the ante here, it would be an alpha squared. But there's an ante here, so we have to think of it as being minus alpha squared. Okay, and what about this one over here? Well, the 1 bar ante. So 1 bar is representing alpha to the minus 1, but we have an ante, so it's minus alpha to the minus 1, plus 1 plus alpha squared plus alpha cubed. Okay, and then when we put them all together, well, let's do it over here. So we just dump them all together. 3 bar, 1 bar, 2 ante, 1 bar ante, 0, 2, 3. Okay, and what is that? Well, now there's some cancellation that happens because in the same mset we're seeing some objects and their antes. So there's a 1 bar here and there's an ante 1 bar. They're going to cancel. There's a 2 and an ante 2. They're going to cancel. The 3 bar and the 3, they're not antes. They're not going to cancel. They stay where they are. So we're going to get a 3 bar. What do we say? These guys cancel. These guys cancel. We're going to get a 0 and a 3. So over here on the polynomial side, we should be getting alpha to the minus 3 plus 1 plus alpha cubed. And I suppose that's reasonable. Okay. So let's do a multiplication. So 2 bar 1 times 1 bar, ante 3. Okay, so in terms of polynomials or polynumbers, this would be, so this one here is like alpha to the minus 2 plus alpha times 2 alpha to the minus 1 plus 3 ante. That's minus alpha cubed. Okay, so at the level here, what do we have to do? We have to make a big mset consisting of all possible sums of these things. All possible sums. Okay, so 2 bar plus 1 bar, what is that? Well, 2 bar is the same as minus 2. 1 bar is the same as minus 1. When we add them, we're going to get minus 3, or 3 bar. So we're going to get a 3 bar. That's that sum. This sum is another 3 bar. We get 2 bar plus 3 ante. Let's think about that. Maybe I could do that over here. So 2 bar plus 3 ante. So the 3 ante you can think of as 3 plus ante 0. Okay? When we do it that way, the 2 bar plus the 3 will give us a 1. So we get 1 plus ante 0, which is 1 ante. So which one was that? That was this 2 bar plus 3 ante. Again, sort of an odd number of antes gives us an ante. But otherwise it's like 2 bar plus 3, so it's like 1. So we're getting 1 ante. So we've done 3 sums so far. Okay, so we have to, now still 1 plus 1 bar. Well, that's 0. 1 plus 1 bar. That's 0. And 1 plus 3 ante, that's the same story as that. The 1 plus 3 is 4, so we can get 4 ante. So what is this telling us? We should be getting 2 alpha to the minus 3. That's that. A 1 plus 2. A 1 ante, so that's minus alpha. And a 4 ante, so minus alpha to the 4. Does that correspond to what we would expect? 2 alpha to the minus 3. Minus alpha, yeah. 2, yes. Minus alpha to the 4th. I think that's right. So it seems as if we have an interesting arithmetic, but now we've used these negative numbers to enlarge our arithmetic or algebra with polynomials or polynumbers in 2 ways. Not just in terms of adding negative coefficients, the possibility of that, but also in terms of adding the possibility of negative exponents. And this is a departure from the usual story of polynomials, okay? And I'm going to talk more about that in my next video, how to think about that. We're going to see some sort of new insights into what the world of polynomials and their algebra really looks like. I'm J Wildberger. Thanks for listening.